Dima, can I ask you to show the screen with your collab file with the incorrect code?
Okay. Which one? The classify KNN or?
Those lines that are already on the screen. No.
Oh,
please.
sorry.
No. Mm-hmm. Yep.
Igor, as the challenge is too hard?
No, but actually I usually Google a lot just to understand what is behind the code, because from the very beginning it's not really understandable which function what's supposed to do. So but from algorithmical point of view, it's like more or less understandable.
Gotcha. Yeah, that's why I'm happy that I started with this lecture and didn't buy this advanced machine learning thing and decided to start slow. And yeah. Now we will talk about regression. I think it will get a bit easier.
One thing I find so annoying about these notebooks is the lack of line numbers.
Oh.
Like sometimes you're trying to find where somebody is in a document, and it's very annoying to.
Yeah. So they have the cell numbers, but not line numbers.
But those cell numbers change. That's just the last executed, right?
Yeah. The order of the execution, and you can have, for example, I have 67 and then 69. And then 70, 72, and you guys probably have different cell numbers either. So
yeah, well, especially since like I'm running it multiple times to try to test how yours it's going.
Yeah, so they are not really good for referencing, saying let's go back to the cell 69, because it wouldn't make any sense for anybody.
There is content bottom on the left, top left. So if you open table content, you can easier find the right place for the.
Oh, now it got.
Yeah, here. But yeah, it is not the best way, of course.
Yeah.
That works if there's a heading inside the view.
Yeah. So you can see that we are done with one part, and then we still have to go through the second part. Yeah. All right, we have few more minutes. So if you guys have any questions, just go ahead and shoot it.
Opening up the table of contents has ruined my my instance of Colab.
Oh, no worries. So it's yeah, it's actually got my collab also for quite some time. So, but that's okay. We finished with this part. The second part, you can just start from there. But we need to go back to lecture slides as well. I just wanted to ask this question. What do you think could be the difference? Why there might be a difference between scikit-learn implementation and our implementation of k-nearest neighbor? What do you think could be the difference?
This regularization, to make sure that it's not outfitted, that I think there is some algorithm in scikit-learn library.
Overfitted. No, it's actually not doing this. It has some stochasticity, so it has some randomness that is inside of this k-nearest neighbor. It's sometimes when you have let's say 10 neighbors, right? But 4 of them say that this is class 1, and 4 say that this is class 2, and the remaining 2 say that this is class 3. So how do you decide which one is that class?
Maybe it's also taken into account the 31, yeah? Which one is closer?
No, but weights are uniform in that case, so it doesn't really take the distance into account. So it has to do something with labels. So how can it work? What is the way? How can it work? Kenneth, what do you think? How would you break the tie?
Coin flip, I guess.
Coin flip, yeah, that would be just a coin flip. So you would just decide randomly which class you choose. If it's equally represented, then you just do coin flip.
But if it's coin flip, then every time you shall get a different result, yeah?
I think it has some pseudo randomness inside, so it does perform basically similar after every run, but between different implementations, it could be different in terms of how do you choose. Because, for example, you can say that I choose the class that has been encountered first. And so, yeah, that could be different. But let me go back to my lecture slides. Okay. So we have finished some part with classification. Now I propose to move on to regression, right? So the following lecture is inspired by the introduction to linear regression analysis, but it's not just about linear regression analysis. It has some stuff about linear regression. So this is just a couple of slides about linear regression. We have independent variable and dependent variable. Igor, which one do we predict, the independent or dependent variable? Which one is we are interested in? But we have a linear regression or just regression?
I think dependent. We are trying to produce dependence from independent, no?
Exactly, yeah. So we are trying to predict dependent variable from independent variable. So in the nature, there are circumstances when two variables can have certain relationships. So dependent means that it's dependent on some other variable. There might be different types of relationships between this kind of variables. One is called positive relationship, in which one of the variables grow and the other variable also grows, right? So we have both variables growing at the same time. Can you guys come up with an example of the positive relationship in economics, for example, when something grows, then the other thing also grows?
Revenue and profit.
Revenue and profit, absolutely. I don't know. I'm far away in the sense I'm not very close to economics. So when I think about economics, I'm thinking like salary and life satisfaction. Okay, something like that. Can you guys come up with a reverse relationship when something is growing and something else is decreasing? So something is growing, but something else is decreasing.
Risk and profit.
So risk is increasing and profit is decreasing. But couldn't that be the other way around? Like you have a high risk industry like space exploration, and then you found something really cool and you got like a profit just skyrocketed. I also have this kind of example, number of cigarettes smoked and number of expected years of life. Sorry for that. So this is my professional, more of a professional. So this is a negative relationship. One of them is growing, the independent variable is growing, the dependent variable is going down. Obviously, linear regression has to do something with line, right? So it definitely works with lines. In order to build linear regression, we need observations, right? We need observations like these two guys, or more observations. In linear regression, we're looking for a line such that it minimizes, what does it minimize, Oleg? What does the linear regression tries to minimize?
Sorry, I have a call.
Go ahead, go ahead. Lena, what is linear regression trying to minimize?
Distances between some points in this line. Like, I don't know how to explain.
Yeah, that's exactly what you're saying. The distance between the point and the line, right? So this is called error. The distance between the point and the line is called error. And the line, the linear regression is trying to make a line such that these distances to all points in the data set are smallest, right? So there are many of these, and their sum should be the smallest. So this is the function that it minimizes, the sum of distances between the line, which is the black y with the hat, and the actual true value of the point. So the true value of the point is in green y and squared, right? So regression line fits least squares method, least squares. So it tries to minimize this, the sum of squares. All right, so coming back to our example with distances and fair amounts. Oh, sorry, the rights, predicting the price of the right based on fair amount, also called fair amount, from the distance of the ride. So depending where you take your taxi and where you're going, right? If you remember that this is how the line equation looks like. It's y equals wo plus w1x. In this very particular case, in this very particular example, Kenneth, what is y hat? What is y hat?
Predictor.
Predictor or prediction, something that you predict. What is it?
Prediction.
It's a prediction. And in this very specific example, what is the name of this prediction? What is it that you're trying to predict?
I'm not sure what the question is. What do you mean?
So it's an estimated fair amount, right?
Oh, sorry,
if you take a ride, taxi ride, this is how much you're gonna pay, right? Simon, what is X in this case? What is X?
The distance.
The distance, right? The number of kilometers that you travel, right? This is how much you travel. Are you taking a taxi from Kiev to Zhytomyr? Are you taking a taxi from Toronto to, I don't know, where, Lena, are you going?
Montreal, Ottawa,
Montreal,
Vancouver.
Montreal, Vancouver, for example, to Montreal to visit Yoshio Benjo. Absolutely. So distances. What is WO, Igor? What is WO? W0.
It's initial amount just to obtain
to
a
sit
car
in the
place.
car, right? Just to
Yeah.
open the door and sit in the car. This is called intercept. Why intercept? This is the base rate. This is how much you pay to get in the car. What is W1? Yeah, well, Oleg is out of the question now. Kenneth, what is W1?
I am back.
You're back. What is W1?
W1 is this factor that gives us the ability to calculate, and mathematically it's the slope of that line.
It's a slope of the line, which can be translated in this very specific example into what? So what does this factor, how do you interpret this factor? And there's an example of taxi rides.
You mean if you...
some dollar.
Fare per kilometer.
Yeah, it's how much you pay for additional kilometer. So this is a slope, as Kenneth said, it's a slope of the line. But also in this very specific example, it's how much you pay for additional kilometer. So if I say I go from 1 kilometer to 2 kilometers, this is how much extra I'm going to pay, okay? This is how the line equation looks like. These are the parts of the line equation. Now we remember what was the function that we are trying to minimize. And in fact, we do it with respect to W0 and W1. So we changed the W0 and W1 in order to decrease the sum of squares. Okay, so we try to decrease the sum of squares by changing W0 W1. And I'll show you how to do it well, with a small example. So here's a small example. There are 5 observations, okay? There are 5 distances and 5 prices that we got for these rides. Now we will compute the linear regression. So we will compute the line together with this equation. First of all, we know from the definition of the linear regression that it passes through a point that is a middle, the mean of first coordinate axis and the second coordinate axis. So the line should go through this point here. This is from the definition of linear regression. If you take the average of x coordinates and y coordinates, this line should pass through this point. This is just, let's remember that. And then let's try to fill in this table here. Right, so we will look for x minus x mean. Igor, what's the value here? What's the value in this very specific spot here in the table? So we try to find x minus x mean. We know x and we know x mean. What is the value here?
2, then 1, then, no, I'm sorry, -2, -1, 0, +1, and +2.
Wow, that was fast. Okay, cool. We do the same for the other side. Okay, Simon, can you give us the numbers?
Okay, this is -2, 0, +1, 0, and +1.
Great, thank you very much. Something a bit more difficult. Kenneth, can you do that?
Yeah, so x minus x squared is -3 cubed 9, I guess.
For this first point here.
Oh, sorry, -2 cubed is 4, sorry.
Yeah, this is 4. What about the next value?
1, 0, 1, 4.
Great, thank you very much. And the last column, it multiplies this column with this column. I wouldn't torture anybody. It's 4, 0, 0, 0, 2. Good. There are names for these two columns. One of them is called variance and the other one is called covariance. But I will not explain it right now. I'll explain it in unsupervised learning lecture. In this one, we'll just sum up these values. So I'll just sum them up, this one and this one. And what I know from literature is that W1 equals this guy here, 6 divided by 10. So this is the slope of the line. This is how can we find the slope of the line. So we know what is W1. So W1 is 0.6. Now, how do we find W0? Lena, how do we find W0? Given that we know that W1 is 0.6, and we know the line equation here. And there is also a hint on the picture here. How do we know what is W0? Kenneth?
So we sub in all the known values. So we use that the 3, 4 and the 0.6, and then we solve for the missing variable.
Yeah. So what Kenneth is saying is that since the line passes through this point of 3 and 4, and we knew that, then we can also substitute W1 with 0.6, and we can solve this line equation for W0, which is missing, right? So this is how it would work. This is how it would look. So 4, which is this value here, equals W0 plus 0.6 that we have just discovered, multiplied by 3. W0 equals 2. Lena, what W0 equals to? In that very specific case, what W0 equals to?
It's too complicated right now.
Too complicated. Oleg, what is the value of W0?
W0 4 minus 1.8. It will be 2 minus. It will be 2.2.
Yeah, it's 2.2 exactly. So this is our line equation. So what is 2.2? Igor, what is 2.2 in terms of taxi rides?
You just pay 2.2. Let's say euro for the car.
To get in the car. To get in the car.
To get in the car. Yeah.
Exactly. Kenneth, what is 0.6?
0.6.
This
Slope. So for 0.60 cents per unit of distance.
Yeah, exactly. Let's return to collab. Let me share my collab. Okay. Here I make a 2D example. So we start with the regression. If, for example, in Kenneth's case, you drop the connection or your runtime has been interrupted, that's fine, because here we just can run this line here. In my case, it's cell 73. You can run it, and that creates a pandas data frame, which has two columns. One is called distance, and the other one is called fair amount. What happens now is that we can reference, so this data frame, in case of a data frame, since it's pandas data frame, we can reference columns by writing example data dot name of the column, for example, fair amount. And you can check it out by typing, running this cell with a fair amount. Now I do some black magic that you don't have to really understand. So just stay with me, but you don't really have to understand it. I'll explain why do I need it. Just run the plotting is in ggplot2 and run this cell with a weird code. I understand it's a weird code. So this weird code makes a plot that looks exactly what we had in the lecture, right? This is, so this weird code is just to make it look like in the lecture slide, okay? Any questions here? Okay, nice. Well, since you don't have questions, please use my lecture slides that you can open in a separate window by going to the website, Moodle website, and find the classification or supervised learning lecture slides, and fill in the formulas for W1 and intercept here for this example data. So example data has two columns, distance and fair amount. So what you need to do is to use these two columns to produce W1 and intercept exactly what we have done right now in the lecture. I'll give you some time for that. Please do. What are you saying?
Sorry, I just talking out loud about it's fair underscore amount.
Yeah, it's a fair underscore amount. Yeah. And please raise your hands in Zoom if you have done it, so that I know that I can move on as well. Just tiny bit of time for yourself to see if you can handle the pandas data frames. So pandas data frames are a little bit tricky, but the main trick I already showed you. You can use dot fair amount, for example, to refer to column fair amount. And you can use dot distance to refer to distance. And you can use my slides to see the formulas.
Could you please switch to your presentation in Zoom, sharing?
Oh, come on! Open the PDF in the Moodle. I think it makes sense because you can have it beside the code, so you can, in your own mood, you can just scroll down and you can see all the formulas and that kind of stuff. Open the Moodle because it has the lecture slides. I don't want to switch because I'll still code in here. I will code here. And since I will be gone and you guys will be facing this homework yourself, then you should know where to look for the lecture slides and all that kind of help. So it's better if we practice it right now. Raise your hands in Zoom if you managed, if you've done it. Anyone? Okay, Lena done it. Kenneth, did you do it?
No, you're asking us just to reformulate the slope of the line expression, solving for
Yeah.
W1 and
Yeah.
W0 using
Yeah.
those other guys. Okay.
Yeah. Anybody else is ready to raise their hands in Zoom? Okay, let us maybe slowly start. Lena, can you help me with typing it? So what should be there in W1?
So we need to compute our x. So it's like example data dot distance minus numpy dot mean. The same example data dot distance.
Yeah, so you can use NumPy.mean, or you can also use dot mean pandas. So the pandas has this nice features. For each column, you can type the dot something like dot sum, dot count, dot head, whatever, and that would do the, for example, mean. Okay, what should we do now?
We need to multiply this to our fair amount. So it's like the
same stuff,
formula.
but for the fair amount.
Yeah.
Mm-hmm. So I just changed that one for fair amount. Okay. Here we go. Anything else?
Okay, divided by.
Divided by. Well, we can use just we can use W1 and then W1 divided by, and then. So what should be there?
Example data distance minus it mean. So.
Okay.
And power 2.
What?
Quadrat. Sorry.
Square.
Square. Okay.
So it is squared. Anything else? ladies and gentlemen, is everything there? And in our code?
Sum?
Dot sum. I guess it's. I think it would be safe to write. Yeah, it could be dot sum. I think it could be dot sum. Let's see if the pandas works out with us. How about this? Do we have to sum this one as well?
Yep. So like in my code, I sum, but I don't know if you need it.
Oh, but in the lecture slides, does it show the sum?
Not, but okay.
Let me show you the lecture slides still. Right, so this symbol here is a sum, right?
Okay.
This symbol here is a sum as well. So we need to sum both of these parts before we divide one by another. But it's all right. Do you guys do you have similar stuff? Oleg, are you having a cold? Igor, where are you guys? We lost you. Simon, how are you doing?
I mean, we don't have a mean for data, the fair.
We can just type dot mean squared.
Yeah.
Oh, you're saying here? Yeah, sure. That was a mistake, of course. Thanks. And also distance, they should be deleted here. But anything else, does it look right? So if I type intercept 0, do we get W1 equal to 0.6? Let's see. Yeah, W1 equals 0.6. So we managed this part. So it looked pretty creepy, to be honest. But it's the way how you can calculate W1 just from the...
Is it not W1 equals W1 is on 2 lines? How does this...
W1 equals W1 divided by some stuff, right? So we basically take this value here, and then we divide it by this value. So we first assign whatever was in the denominator. So if let me show you the slides.
Because I guess because you're rewriting what W1 is in the second line. Okay, all right.
Yeah.
I understand now.
Okay, gotcha. Oleg, did you get the intercept as well? Can you help me with the intercept?
Intercept. Wait a moment. Intercept. It shall be. Actually, we found this. We need this average fair amount, yeah.
Okay, so example data fair amount mean. Okay, then
fair amount mean. Then wait a moment.
Simon, can you help us? What happens afterwards?
So yeah, where are you?
Minus
average distance.
Minus W1 multiplied by average distance.
So example data dot distance dot mean, right? So if I run this, I can see that my W1 equals 0.6 and intercept equals to 2.2, which is supposed to be like this. Yes?
Mm-hmm.
Does this, now everybody, does this make sense? Does the programming of this stuff make sense? Does the theory of this make sense? Can it? Does it all make sense?
Yeah, it does. Yeah, once I understood that those 2 lines you're overwriting a value, yeah.
Yeah, I could have inserted this whole thing instead of W1 here, but the line would be so long that you wouldn't see it.
Yeah, I understand that. Yeah.
All right, so let's visualize this line, right? Let's put it on this canvas. So now we created the canvas with points. Let's put a line that we have just computed. So we computed the slope and the intercept of the line. Here we can say, hey, take this canvas here and add a slope, a line with a slope and intercept, and color it black and make it dashed, okay? So it just takes the canvas and it creates the line with an intercept and W1 as we have just predicted. Okay, now what if it's a wrong line? What if we have made a mistake? How do we know if we made a mistake? Oh, but we just look for what the computer thinks about this line. We say, okay, make this line, but now also add on top of this line a line that is predicted by a method called linear model. And just let's see which one is right. I mean, let's just compare them. And it looks like these lines overlap perfectly, right? So whatever we have computed makes sense, makes computational sense. All right. Now we go back to the lecture slides. Okay. Wait a second. Okay, so this was a linear regression, a short introduction to linear regression. Now, the linear regression is a very nice algorithm when it comes to the relationship between independent and dependent variables, linear relationship. When it's linear, it's all nice and great. The problem starts when the relationship between independent and dependent variable are clearly not linear. Like in this case, for example, it is clearly a quadratic relationship or a paraboloid relationship, but it's not linear relationship. So in that case, linear regression becomes, well, not very useful, right? So we need to use something else, not linear regression, but something else. And I wanted to discuss a decision tree algorithm. I also know that you have been given the decision tree algorithm, but I kind of still have a feeling that it's nice to, iterate over it and just to make sure that everybody is on the same page. So what the decision tree algorithm does, it's asking questions about the value of independent variable in order to predict the value of the dependent variable. So here are our points. This is our distance and fair amount as it was as we used before for the linear regression. And what we do is we have a question about the value of independent variable, which is distance. And then we have two outcomes. So we can have, if the distance is smaller than x, we predict price y. If the distance is bigger than x, then we predict price zeta. These are called, so the pink one called root node, which has a question to the independent variable value. And these two green guys called children, right? The left child is the one that predicts Y price, and the right child is the one that predicts Z price. These are called leaves, right? So there are children, and also you can call them leaves of the tree. You can see that there are two children of the tree, and that's why it's called binary decision tree. The binary decision tree. There might be trees that have more than two children, but we are not going to discuss these. Okay, so now that we have discussed that, let's imagine that x equals 2.5. Just this is my like a random guess. Let's say that x equals 2.5, just out of blue. I will explain later where this x 2.5 comes from. But first, for now on, let's just assume that it equals 2.5. Now, I would love to ask you to tell me what are the good values for y and z. So let me come back to this and say that the decision tree that we are building, it has a split at x 2.5. So whatever traveling we have done that is shorter than 2.5 kilometers, So if you take a taxi for less than 2.5 kilometers, you will pay Y dollars. If you take a taxi for more than 2.5 kilometers, including 1,000 kilometers and wherever you like to go, you will pay Z fixed price, Z dollars. Okay, this is a very simplistic example. It's very naive, doesn't make any sense, but this is just a way to think about decision trees. So what do you think in this specific case would be good values for Y and Z?
Well, you could take the mean of the two and have 3 and 4.5.
That makes sense, provided that we are trying to minimize squared error, right? So we are trying to minimize this, the distance. Well, basically, we're trying to minimize the error. So first question that we should ask ourselves is, what does it mean to be good? What does it mean for values to be good? And then I would say, let's minimize the total mean squared error. And then you can say, well, exactly as Kenneth said, that taking the averages. But before we take the averages and go with the clever way, Kenneth's clever way, we will do Dima's dummy way. Okay, let me do first the dummy way, because we'll first calculate the MSC and see what does it make, what does it mean, and then we will do the clever way. So first, let's calculate the MSC. So these are the real values. The green Y is the real right value, and predicted is how much we predict, right? For these two rights, we predict $4. So it doesn't matter if it was this one or this one, we predict $4. For these three rights, we predict $5. Okay. Do you guys have any questions? Okay, that makes sense. Now, what we do, we actually calculate the MSE for these two values and that split of 2.5. So what I do is I just say, okay, for the first point, the real value is 2. The predicted value is 4. So it must be, well, 2 minus 4 squared. How about the second point? Simeon, what are the values in the second point case, in the case of the second point?
Second point is close to 0.
Well, close to 0, or is it 0? So this one is 4. It has a real value of 4, and its predicted value is 4, right? So it must be 0.
But it's 0
sorry?
It's 0 squared, so it's
0 squared. So yeah,
a little bit bigger.
Sure, absolutely. It's a bit bigger. It's squared. Definitely a bigger amount. Igor, what about the third point? This Y3 and Y3 hat. So this point here.
I'm sorry, I was interrupted by another.
So look at here. Look here. Get back on track. So what we do here, we calculate the difference between the real value of the point, which is a green Y here. For this point, the real value is 4, and its predicted value. So for each point in this subspace, we predict $4. So it means 4 minus 4, right? So the real value is 4 because it has the Y-axis equals 4, and the predicted value is 4. Okay. Now my question is, what's the value? What's the predicted value for this point? So for each point on this side, we predict $5.
So 5.
So then 5. What is the real value of this point?
Yeah, 5 also.
5 also, so it's 0 as well, right? So here you're back on track. Oleg, what about the fourth point? Oleg?
Hello?
Hey.
So fourth point, this is a 4, yeah?
Yeah, the Y4 and Y4 squared.
Yes, then it will be 5 minus 4, 1, it will be 1, yeah?
So it's, okay, tell me, what is the real value of the fourth point? What is the fair amount of the fourth point?
4.
4. What's the predicted value?
5.
5. So it is 1. And the last point
Yes.
has also 5 minus 5, so it's
Yes.
1. Oh, 0, sorry. And then we just basically for the first point it's 2 squared, for the second it's 0 squared, 0 squared, 1 squared, and 0 squared, right? So we get all these things together, and then we take a square, which is 4 plus 1, so it's 5 divided by 5. Oh yeah, by the way, there has to be this 1 divided by n. So 1 divided by n is 1 divided by number of points in the data set. Okay, so it's 1. So here what we say. We are saying that if we split this data set by 2.5 distance, meaning that if the distance is less than 2.5, we predict $4 price. If the distance is more than 2.5 kilometers, we predict $5 price, whatever high the distance is or whatever small the distance is. With and this split and this decision tree has MSE of 1. So this is the error metric, how much we are off the target, how much we mispredict. Does this make sense?
Yep.
Everybody? Okay. Now the next logical question would be what? Kenneth, what would be the next kind of thing that you can improve in here?
I mean, try to get a lower mean squared error.
By for example, doing what?
I mean, my first suggestion is to take the mean of these points.
Yeah, you can take yeah, you're somewhat jumping ahead of me of my talk,
Sorry,
but this
okay.
would be somewhere we will come to. We can find better y and z, better y and z. So instead of having 4 and 5, we can have something better. Lena, what would you suggest? How would you suggest to change 4, for example? How would you change this y value to lower MSE?
Good question.
Igor, what would you suggest to change the y value here? So now it's 4. Here, this is 4. But how would you suggest to change it to lower the total error? Any wild guesses?
Well,
Let's say it's fine.
let's make it maybe, I don't know, 4.5.
4.5. Hey, let's do it for, oh, sorry, not for 4.5. Let's do it 3. I was close, but 4.5 was in the same direction as I was thinking about. So let's make it 3 and see what happens. All right, let's make it 3 and see what happens. So what happens with if we make it 3, we calculate absolutely the same MSE, the same way we have done it, but just now for this for both rides that were below 2.5 kilometers, we predict $3 instead of $4. Okay, and we got instead of 1 MSE, we got 0.6, which means we got better MSE, we got better algorithm, we have a more accurate algorithm. So we can say that if x equals 2.5 and y equals 3 and z equals 5, we get a lower MSE, we got 0.6. Is there a way to improve still? Oleg, what do you think? Is there a way to improve? By changing, let's say, y or z? Which one we can change to improve?
Which one we can try to improve?
For example, if I would lower this one, if I would predict not 5,
yeah.
but something less than that, would that make sense?
Yes. We again can try to make this average here, 14 divided by 3. 14 divided by 3, it will be 4 dot something.
4.66.
Yeah.
Exactly. You're right. It's 4.66. And if you calculate it, you get 0.53, which is even lower than 0.6. All right. And this is what exactly Kenneth was saying in the very beginning. He was saying, guys, don't waste your time. The right thing to do is to take an average from both sides, right? And that's what we ended up doing, actually taking average. It's this one, 2 plus 4 divided by 2, 3. And then 5 plus 5 plus 4 divided by 3 is 4.66, right? And this is what we have. Kenneth, now since you were a prophet here, what shall we do now? We have this MSE of 0.53. Do you think it's the best thing we can have?
No,
Else?
we should charge the highest fair amount of in each category. We should charge 4 and 5. So we guarantee to make profit on every trip.
Oh, this is a businessman talking now. But what if we are trying to lower the MSE, not get profit? I mean, it's not unnatural. I understand, but
Sorry, so you asked me about profit, so I answered about profit.
no. So let's consider the MSE. So what else can you do to make this tree work? Has a smaller error, to have least error.
You can shift the X decision.
The split, yeah, you can shift the split, right? So in the beginning, I was saying, let's just trust me, guys. I know the 2.5 is good, but why do you trust me anyway, right? You shouldn't trust me. We should actually look it up and see what the other splits have, right? So how did we choose the split on the first place? Well, there is no good reason. There is no really good way to do it besides just trying all the possible splits, right? So we can actually try all the possible splits. Kenneth, I would love to see the limits of your expertise. So tell me, what are the possible splits in this case?
I mean, well, you could do a cluster of 2, 3, 4, 5, and then split at 2.
Okay, that's true.
1 and then 2, 3, 4, 5.
Okay.
Yeah, I think, or then what else?
Can you split 1, 2, 3, 4, and then 5?
I mean, you could do whatever you want to, yeah. And I mean, you could look at what average would give you, but I think that would just give you 3.
No, but what are the all possible splits? All possible. How many there are all possible splits? Simeon, how many there are all possible splits in general, in principle, in the entire universe?
N minus, I'm sorry.
I think it is 5.
5, which is 1, 2, 3, 4. Where is the 5th one?
Just. Yeah, you're right. Okay. It's 4, in fact.
N minus 1.
N minus 1.
Yes, you're right.
But I can actually claim, and I will claim, that there are 6. Who would agree with me? Do you guys see 6?
Well, yeah, there's 2 empty sets, below 1 and above 5.
Yeah, right. So these are the possible splits, right? Igor, what do you think about the first and the last one? So if are these meaningful? Are these useful? Are these splits useful? So if I split here, why would it not be useful?
Because no evidence between 0 and 0.5 and after 5.5.
Yeah, so there are no observations. I'm not really splitting my data into any reasonable chunks, right? So I don't really have to look at these. So in fact, we ended up having just 4 possible splits here. How do we know which one is the best? How do we know which one is the best? Lena, how do we know which one is the best?
We need to calculate for everyone and
we could calculate what?
MSE.
Yeah, we could just calculate MSE for each one of them, right? And see which one works best, which one has the lowest MSE. Oleg, what was the MSE of this 2.5 split here? Do you remember what was the MSE that we calculated?
0.506, something like this. And
0.53, yeah, 0.53. So we already know this one, right? So this one we already know. Let's check the other ones. So if we work with Kenneth's law of Kenneth, so he said that let's use the mean of both sides. So we trust him. He seems a very reasonable person. So one side is $2, the other side is $4.5. And then we calculate the MSE of this split, and it turns out to be 0.2, okay? Then we look at the other split here, and we calculate the split. So in this case, we would have to predict $3.6 for one side and $4.5 on the other side. It would be 1.03 MSE, and the last one would be about 0.95, right? So obviously we take the one that has the smallest MSE, and we split based on this MSE, and then we predict. So for the distances that are less than 1.5 kilometers, we predict $2 price. For the distances that are over 1.5 kilometers, we predict $4.5 price. Okay. Is that all? Can we do better? Can we still do better than 0.2? Any ideas? How can we do better?
Add a second split, I guess. A third leaf.
Add a second split, so we can go down there. We can actually make it deeper. We can go ahead and make it deeper. Yeah, so we can make the MSE even smaller in that case. So let's return back to the collaboratory. Let me shift it here. This would be the final part for today. So I just wanted to go through quickly this decision tree algorithm here. In fact, we will use the scikit-learn library called decision tree regressor. There is also decision tree classifier that exists up there, but we will use decision tree regressor. Change your max depth equal to 1. Everybody, change your max depth to 1, not 5, to 1. And run this cell, and run this cell. What happens now is that I take the decision tree regressor, DTR, and I fit it on the training data, and which is our example data. So I take the distance. I do this weird reshape because it somehow doesn't work with pandas data frames. And I say that this is my data, the distance is my data, and fair amount is my labels. This is what I want to predict. Okay, does this make sense? The fair amount is what I predict, and that's why it goes after comma. If I just can write y equals 2, and here I can write x equals 2, so that you can, it is more verbal, right? So x is my data, which I use to train my algorithm, and y is what I want to predict. Okay, so I train that. Here, I do something weird. I want to visualize the predictions of the decision tree. So what I do, in fact, is I create a synthetic test set. I create a synthetic test set in such a way that I have all my distances covered. So I create a test set in such a way that it would cover the entire space. I will show you what does it mean in a second. Just run these two cells and make a plot. So here we go. Basically what I have done, I have created a test set on top of our training data. So this was our training data, 5 observations. We trained the decision tree, and then I created a test set that would consist of point grid that would cover up the entire canvas here. The color of each of these small points, there are tons of points here and there so that they cover up the entire space. The color of each point is the predicted value by the decision tree. So the decision tree predicts a value for the right for each of the small points that are beneath the green points. And I color them up based on their right value, okay? So if you look at these graph and my lecture slides, this is exactly what we, and I will do it for you guys so that you can see it more clearly. So if I come back to my lecture slides, and I'll show you what we have decided to do. We have decided to predict fair amount 2 for every ride that is less than 1.5 kilometer, and fair amount of $4.5 for everything that is more than 1.5 kilometer, okay? So remember that one, and let's look at what we have from our scikit-learn library. Okay, does it look similar?
Yep.
It's the same stuff, exactly the same stuff. So 1.5 is somewhere here. then everything that is beyond has a value of 4.5. You can see it on the scale here. And everything that is below it has a value of $2. I have a question to you guys. Does anyone know why do we split in the middle? Why don't we split and let's say to 1.6 or 1.55 or 1.49? Why do we split in the middle? Why the line goes through the middle? Anybody?
Our data set are integers for some reason, so perhaps that's a reason. I don't know.
Yeah, could be, but the split is not an integer value, right? Split
Yeah,
is 1.5.
Because we wanted the space between the integers, the data set.
Yeah, you wanted to have equal distance to the opposite classes, opposite spaces, right? So you are assuming that this space can be used for other points like the same value to fall into, right? Ask me questions, please, ladies and gentlemen. I feel like there is some kind of misunderstanding, so or something that is not clear. Make sure it is clear. Igor, do you have questions? Sorry.
What's the answer then? Why it's 1.5? I didn't get.
So the answer is that basically you're trying to make as much space that would separate these 2 points, right? So there are 2 spaces, 2 leaf nodes, one and the other, and you're trying to make sure that you have the maximum space that separates your decision boundary from one and the other leaf nodes.
Okay, so we have 2 spaces. That's why the maximum distance is just divided by 2 between.
Yeah, it doesn't. So let's go up here and make the max depth equal to 2. Let's say 2, right? And run the same cells over again, right? And see what happens. Igor, can you try to interpret what the hell this picture means? What does it actually say?
Well, it says that actually for distances up to 1 kilometer, one like algorithm or one
split
per amount output for distances from 1.5 kilometers till 4.5 kilometers. We have another fair amount, so another like mathematics behind the calculations, and actually we have one like how to say outstanding amount of 5 kilometers that and actually this distance has another logic of fair amount, so it's like that, I think.
Yeah, it's so this tree has 2 splits, right? So it has one split that is on 1.5 as it used to be, and now the new split is at 4.5. So we have 3 buckets, 3 leaves of this tree. We have one that predicts 2 distance, the $2 for the distances that fall into this bucket. We have the second bucket that predicts about something like 4.66 or something like this, or actually less than that, 4.33. And the other bucket that predicts 5, right? So we have 3 buckets, 2 splits. That's the way. Simeon, I want to ask you a question. So when I change this max depth to 5, how would you assume this picture would change? So if I would allow 5 splits, actually 4 even, that doesn't really matter. Even if I change it to 4, how would you assume this picture would change?
I think that every point will be in separate cluster.
Exactly. Do you guys see? So let's do it. So let's make max depth equal to 4, and okay. So here we go. So each point is in its own place, as it's in its own bucket, and each bucket has its own prediction value, right? How do you call this kind of algorithm that has not super nicely predicted the training data?
Overfit.
Overfit.
Yeah, it's called overfitting. This is overfitting. So one of your homework exercises would be to do the same coloring, but for linear regression. Try to do the same coloring for the linear regression. So this exercise would be basically just copy pasting these lines here and there and just making sure it's the same stuff works. Okay, so you would color, you would make the same coloring for this algorithm here.
May I ask a question?
Sure.
So in principle, regression, this is a predictive tool. But decision tree, it's also predictive then?
Regression is a family of algorithms which is decision tree part of. Okay? You have a family, it's called the regression. And decision tree regressor is one of the algorithms that are part of the family. You can have linear regression, k-nearest neighbor regression, decision tree regression, and you can have random forest regression. You can have many regressors, but decision tree regression is just one algorithm out of many that is part of regression family. Regression is about predicting continuous value. It's not about specific algorithm. It's about being able to predict the value, for example, of the right? Classification is about predicting classes, about categories. And there is also a decision tree classifier, right? Classification, right? So you predict, did I say something wrong? But anyway, classification is about categories. And there is a decision tree classifier, which is part of the classification family, right? Does it make sense?
Yeah, and this is a decision tree. What's the usual business case for this?
For this algorithm?
Yeah. Because usually I saw only linear regression, yeah, but let's say decision tree was like a theory, yeah, but I never saw it, yeah, in real life application.
Isn't it for when humans have to apply apply it afterwards? Like, isn't that kind of the purpose of decision trees?
No, so ladies and gentlemen, think about this in the following way. You have a tool set, right? You as a machine learning expert, you're trying to solve a problem. Let's say you're trying to predict profits of your company for the next season, okay? Here we go. You have tons of data about your company. You have number of people you have number of customers, you have a number of high paid customers, and so on and so forth. What you're trying to do is you're trying to predict your profit of the next quarter. You have tons of, you as a machine learning expert, you have a lot of tools that you can use. One of them is linear regression. One of them is decision tree. Another one is random forest. The fourth one is the neural network, and so on and so forth. So all these methods can be used to solve the same problem, like predict the profit of your company for the next quarter. But they all have their own peculiarities, if I may say that. Linear regression is very transparent in a sense that it will tell you exactly the weights of each of the features that you have. For example, your profit may heavily depend on the number of staff members in your machine learning department. So more people you have in the machine learning department, bigger your revenue. Sorry for that. I don't know if it's true. But so this is, but the linear regression will work nicely only in case there is a linear dependency between number of people in machine learning department and your revenue. It may not be true. It may be some kind of quadratic dependence. So let's say adding one more person to the half of the people into the machine learning department, it wouldn't mean just a linear interpolation, linear increase in your revenue, but it would mean a square increase in revenue, exponential increase in revenue. then you need something more sophisticated. So decision tree is more sophisticated tool for solving regression problems, okay? So imagine yourself having a toolbox, and in this toolbox, you can take out the regression, linear regression, sorry. You can have decision tree regressor, you can have random forest, you can have neural network, and so on and so forth. You can use them on regression problems, and you can solve regression problems using different tools, but they all solve regression problem. They predict the continuous value.
Yeah, but what's algorithm to select which tool? Yeah, so this is the.
This is a central question. Yeah, this is the central question. Sometimes it depends on your problem. It depends on how much data you have. For example, if you have little data, then the linear regression probably would work better because linear regression does not require too many data points to train. Neural network requires heavy amounts of data to train. So you need to keep these kind of things in mind. Decision tree and linear regression are interpretable models. So you can say, for example, in this case, I can say, if the distance is less than 2.5 kilometers, we predict this price, right? This is very interpretable. In the case of neural network, there is no interpretability. You can't really say if this and then that. There is no way you can say that. There is no way. There are plenty of attempts, but it doesn't really have yet this very clear way to open up the black box. So you have to, as a machine learning expert, you should really look at all these things at the same time and find the best tool that it works for you. It also can you can also aim at the lowest error, right? So you may just be willing to accept any algorithm that produces the smallest error, which is fine, which is another way to choose. Okay.
But and when you look at examples of decision tree, like they very often they seem to be like rooted where you have lots of data to make decisions and yada yada, but then in like the factory floor implementation of things, the person using the model doesn't have that much data in front of them. It's a human being can just look at a chart and use the machine learning to make all these decisions. A human being can look at a chart afterwards or go through a flow chart or.
Yeah, exactly. So you can interpret the decision tree. You can see what are the rules that decision tree has, exactly like we had in the lecture slides, right? So if I go back to my lecture slides to my decision tree, this one here, this is a decision tree that you can come up with, right? And this decision tree is absolutely transparent. So you can say that everything that is every ride. For example, I have worked with the Bolt company. Do you guys know the Bolt company? They have taxis, so operate taxis. So if you take a ride for more than 1.5 kilometers, you should pay $4.5. It's very, very simple to decipher this tree. Well, if you have a neural network with millions and millions of nodes, it would be hard to actually, for a human being to look at the neural network and say that the neural network has that rule or this rule, that kind of stuff, okay?
And does it work also with multivariables, the decision tree?
The decision tree works with multiple variables. It works with multiple classes. It works with multiple, it basically is very universal, as well as a linear regression. So most of these algorithms that we will be looking at in this course are very multi-purpose algorithms. So you can do regression, you can do classification, and all that kind of stuff.
Okay, thank you.
It's a very important question, so please ask me these questions. And since I don't know exactly specifics of your field, your interests, it is very important that you guys ask me these questions. Any more questions of that kind, any kind?
It would be interesting to compare the same data set, like linear regression and decision tree, yeah?
Exactly, Oleg, and this is exactly what we are going to do. Not in the remaining 10 minutes, but in the remaining 10 minutes, what I'll do, I'll spend some time just making sure you guys have everything set up for tomorrow. Because tomorrow, we are going to do exactly what you were saying, comparing different models on the same data set, all right? And seeing which one works better. So this data set is called New York City Taxi data set, right? So this is data set that we are going to use. And what you can do, you can actually run this code here. We will have to rerun it tomorrow because your run times will be down. So we will start from here tomorrow, but just that you know what's the procedure. If you run this cell, it will tell you I need a verification code. So if I click on this line here, it will ask me for account. So it will say, hey, could you choose your Gmail account? And I say, well, take my default Gmail account. So I say allow, and then I copy this code here. I copy it into my keyboard buffer. I go back and I paste my code inside this box. Igor, is everything fine? Can you follow that?
Yep. Yep.
So you just you did that.
I'll spend several hours, I think, just to complete all the stuff, just to understand, because I need to like to look through the code and then to try to understand it better.
Okay. Okay. But this does not require any understanding. So here I don't know what this code does myself. This is just a basic copy paste from the Google pages. How do you get stuff from my Google account to your collaboratory virtual machine? All right. So it doesn't really need any understanding. I don't really know myself what the hell the code does. I just needed to get your to download the data. Okay. So I downloaded the data here. I just ran this stuff and I downloaded the data. I don't know what the code does, and you don't need to know what the code does. It's just basically Stack Overflowing. You guys know what the programming is, right? So the legal name of the programming these days is not programming, it's Stack Overflowing. Nobody programs anymore. Everybody just Googles. And when they Google, they find Stack Overflow suggestions, and then they just copy paste those suggestions. So don't be a hero, just copy paste, and some of the things you don't really need to understand deep. So this would be the, can you guys raise your hands if you see the output, these two files? Oh, sorry, this nyc-data.zip. If you see it, please raise your hand. You can raise a physical hand, or you can raise your virtual hand. You can raise both hands. It doesn't matter. Oleg, did you make it?
I think so. Yes, I have it.
Simeon, do you have it? Okay, what's the problem?
No, it's just I just started to push to run the cells.
Okay, Igor, do you have it?
Right now, I'm trying to enter verification code.
Okay, gotcha. Does it work? So you should see nyc-data.zip inside your file directory. So if you run !ls, then you will see nyc-data.zip. Somebody has this nice clock in the kitchen that has this, that does this. It's pretty funny. Igor, can I help you somehow? Simon, do you have it?
Yeah.
I have it, okay.
It asks me for verification code and I give it, but actually...
You should press enter. You should press enter.
Yeah, it gives me verification error, but if I try to enter this link, like pasting into browser, it allows me to see. That's something strange.
Okay, but you can maybe do it tomorrow because we don't need it right now, because we will need it tomorrow just to set it up. So you can guys unzip the stuff. You can unzip the stuff and you will see that inside this New York data zip, we had train 2 million CSV, we had model pickle, we had test.csv. So these are the things that we have, and sample submission.csv. So these are the 4 files that you should have downloaded. And also you have Mac OS X. This is hi from my Mac. I don't know how to not to put this stuff into the files. So sorry for that. But this is your virtual machine somewhere in California, so there shouldn't be any real harm done. So these are the files that we are going to use tomorrow. It would be nice if you can tomorrow before the lecture you can run these stuff and get it into your virtual machine. Another thing that we'll be using tomorrow is the Kaggle accounts. Do you guys have Kaggle accounts? Okay. Okay. Igor, do you have a Kaggle account? Do you have an account on Kaggle?
I think yes. For one lecture, as far as I remember, I created one.
Yeah, cool. So that should be fun then. So you go to the Kaggle.com, or let me go to the Kaggle.com. So here's the New York City Taxi Prediction Challenge. I'll send it to chat, but I know it will disappear, so you guys click on it. So this is a New York City Taxi Fare Prediction Challenge that we are going to work at. And now you can press at the top window, you can press on your face, on your account, and you can choose My Account. And if you go down there, you can create a new API token. You should click on this link, create a new API token. If you click on My Account, so you should have, from the link that I sent, you should have, go to the top right corner. There is a small circle with your, whatever the animal that is there, or your image. Depends if you have used your account or you haven't used your account. Then you can click My Account. I'm a competition expert, by the way. Self-advertisement a little bit. And you can click on Create New API Token. This will create this will actually make a file. You will download a file. So it's called kaggle.json. If I look inside the file, I will look inside the file. I will see, so let me, I can see if I can share it. Okay, you can share it. Now you can see my entire screen, my desktop. So you can see that there is a username and key. You need both of these things. Okay, no. I should open it with Sublime or something like this. So I have a key and a username. And if you go back to the collaboratory, you will see that you need to enter your username, your Kaggle username, and your key. After this, we can work tomorrow as soon as you have done that. Okay, so you should enter your username. For me, it would be Skyfallen, and my key is this thingy here. So it's you should do it for tomorrow. Okay, and tomorrow we will get back to this, and we will run through the rest of the code. Okay. So that's all for today. I think I have already overwhelmed you enough. Tomorrow we will complete this this lecture, and we will start a new lecture. I'm thinking that maybe it makes sense to go with unsupervised learning rather than regularization. As far as my feeling goes, it makes sense to go with unsupervised learning. I hope that you guys share my opinion. What's your, do you have any do you have a strong opinion about this? Kenneth, do you think that you would benefit more from unsupervised learning, which includes PCA, TSNE, and 3 clustering methods, than about regularization, for example, L1, L2 regularization, dropout, and that kind of things?
I'm going to go along with my colleagues. Either is fine.
No strong opinion about this.
No strong.
Okay.
Like the first is interesting, but I mean, no strong opinion.
Okay, gotcha. Semyon, what do you think? Just quick show of hands.
I remember L1 and L2 from Roman Ko's course, so that is why I think
okay,
if you're going to go deeper in the subject.
I'm going to go deeper than Roman Ko for sure. I have seen Roman Ko slides. I think it's nice, but I think they're too mathematical for me. I wasn't able to follow all the time. So I think it would make sense, but it also depends on your interest. So if you feel that unsupervised like clustering methods and dimensionality reduction may be more beneficial, then I'm flexible enough to change that and change it into unsupervised learning lecture.
Sounds like.
Sorry, go ahead, finish it.
Yeah, I mean, sounds like clustering is more useful.
Okay, Lena, what's your take on this?
I know that it's really difficult to understand regularization, and I have problem with this, but if you can share your slides, for example, and I can go myself, so it's fine. And
okay, you are a regularization person. Let's put it straight. So you want to know about regularization. Gotcha. But there's nothing wrong about this. Oleg, what's your opinion about this?
I don't know. I don't have a strong opinion. Yeah,
okay, you go with the other colleagues.
Yep.
Okay, Igor, what's your opinion? Igor said that
he had to go. He had a hard.
Yeah. Okay, hard. You left me with the tie then.
So in fact, if everybody 50-50, then Olena decides.
Because she seems to have a stronger opinion.
Yes.
Right? Okay. Then let's go with the regularization. I will share the unsupervised learning slides, and you guys, I'll share all my slides, the ones that I given in the other course. So you can. I also suggest you to look through the deep learning slides, because I checked the deep learning course. I wasn't impressed by the Blackboard stuff. So I would really suggest that you go through these slides as well. But let's tomorrow then, after we finish the supervised learning, let's go started with regularization methods. Thank you very much for being today. You survived 4 hours straight. It's incredible. So I'll see you tomorrow. Talk to you tomorrow. Yeah, bye and have some rest.
Okay, thank you.
Can
I ask a question?
Yeah, everybody, you can go and just, I can stay up and talk to you if you need to.
Because when I execute this line, mkdir kaggle, yeah, so it seems doesn't work. It's this one.
No, it will work. This one is fine, but there is this problem here. Here it says that it's some kind of no such file or directory or something like this. I don't know what exactly the problem, so I usually do it like this. I run the next cell and then I go back and it starts to work. I don't know what the hell is wrong with it really, but that's how it works.
All right, because I was having the same problem.
Yeah, I had the same problem and I don't know how to solve it. So the way how I do it is I go forward with the cell and then go back and rerun this stuff. But that's the official Kaggle configuration file. That's how they officially kind of say that this is how you should configure Kaggle API. So I don't know what's wrong with them. Or is it virtual machine? Something is wrong, but I don't know exactly what.
Strange, because the first line, it tells me mkdir cannot be created.
Oh.
Cannot create directory Kaggle, file exists.
That's exactly that.
That's because probably you already had it, right? Or
yeah, I think just because a previous instance of it exists. Yeah.
No, it's just you already created it, and it's just repeated. And once you repeat it, it says that but it's already there. So it's no problem. This is no problem. Just go ahead and run the others, and you will see that with the CP line, it also has an error. But then you have to go one step further, run the next cell, and then go back and rerun the whole sequence. Not the whole sequence, but starting with CP line.
Mm-hmm. Okay. Okay, thank you.
And you should do it tomorrow as well, because you will have your runtime disconnected and everything will be lost. So this is a problem with Collaboratory. Everything is get lost once you close your computer and go to sleep. And it goes to sleep as well. So anyway, thank you very much. It was a pleasure. I hope that you guys learned something, and I'll see you tomorrow and talk to you tomorrow. And
okay.
Lena, I don't know how you're going to survive that stuff. So
I don't know.
The sun is up.
See you tomorrow. See you tomorrow.
Bye-bye.
See you. Bye-bye.
Bye-bye.
Bye, guys.